here's the problem. You have a graph where each node is somebody who's, I think they were playing tennis. Doesn't really matter. And you take each pair of people are going to do a competition. And they're going to play tennis, obviously, because they're tennis players. And somebody will win. All right? So now you have the graph which sets for each pair of people, there's an arrow which tells you who won. And what is our task? Our task is to find an ordering of the people such that every we're going to ignore all the other edges, but every consecutive pair of people has the arrow going in the right direction, right? We're basically looking for a path, right? So a path starting somewhere that goes through and reaches every person, right? And how do we do that? Well, more of the output, what you would think you would do is try to do more of the output. And what would that say? It would say, well, suppose the loop invariant, right, is that more of the output would say, I've produced some of the output already. And what's the output? It's a path. And now I have this path, and what do I have to do is I have to extend the path, right? But maybe all the arrows, I'm at some node, and if all the arrows are coming in at me, then I'm stuck, right? So that's where kind of more of the output, where you're kind of building your output like that, it seems to fail. Does that make sense? Because I want to keep building it forward. But instead, if I switch over to more of the input, then what does the more of the input say to me? It says to me, I have some of the input. Well, what's my input? My input's a graph. So does that mean I have some of the edges? Well, I don't know. It's weird to have some of the edges. Let's say we have some of the nodes, right? So let's say we're considering the first so many people. And I'm considering all the edges between those people, all right? So the input is a big graph, but we're going to pretend that we have the smaller graph, which only is the part of the graph considering the first I people. And now there's no particularly order on these people, right? They're not the best people. They're not the worst people. We put the people in a random order because we have no order of the people yet. And all those, I hear all these beeps. That might be my Discord program. Anyway, so and what does the loop invariant say? It says, let's pretend that we have a solution to that, right? So here in, look at picture A, ignore the V for a minute. Picture A, I have a path that goes through I of the nodes, right? And here I enabled them 1, 2, 3, 4 up to I, but they might not be in that order. They're not. We don't know what order they're in. I consider the first I nodes, and I have a solution for the first I nodes. They go in some order, and there's the order. That's what we have. Is our loop invariant gives us to us. Everybody understand what we have so far?
Yes, Professor.
Right. So now if I'm doing more of the input, what do I need to do? I have to say, okay, I got to make my input bigger. I take down the next node, right? And the next node is what I'm going to call VI plus 1, right? I have a solution for the first I nodes, and I need a solution for the first I plus 1 node, so I consider the I plus first node. And we're going to have 3 cases. One case is that the new node happens to have an arrow that is directed towards U1, right? In that case, there I have a new solution, right? Everybody see that's just my new solution. It was such an easy case, but I'm done with that case, right? People see that? here's case B. What's case B is there just happens to be an arrow from the last node in my solution to my V, in which case I have a new solution, right? Everybody see that? Now, what's the third case? Well, to get the third case, for every node U, right, all of these U's, well, there's either an arrow from U to V, or there's an arrow from V up to U, right? That's the property of our graph, right? We know the arrow goes one direction. For every U, it goes either towards our V or away from our V, right? So I like to think if it's going towards the V, like it is in the picture here. Oh, and what do I know? In case A, it's going towards the U, and I'm assuming it's not case A, right? If it's not case A, then it's going from U to V, right? And it's not case B, so we know that the last guy, we have a node from the V to the U, right? How do I know that? Well, because I know it's not case A or case B. How do I know it's not case A and B? Well, if it was, I would be done already, right? So that's one thing we can often do. All right, so now, suppose by some miracle in case C, we have some node along the path, uj, and it just so happens that there's an arrow from uj down to V, and then there's an arrow from V back up to uj plus 1, right? See how we have that in the picture? Now, if we had that by some miracle, then we would be done. Why? Because our new solution would start at U1. It would follow the old solution up to V to uj, and then it would slip down to V, and then it would slip back up to the next U and continue on, right? In some ways, this is kind of like insertion sort. How do you do insertion sort? Is the first I numbers are sorted. Now I take the next number and I need to insert it where it goes. Where does it go? Well, it could go at the beginning. It could go, if it's really smaller than the first number, it goes at the beginning. If it's bigger than the last number, it goes at the end. Otherwise, I search for a place where it can go in between and I can slip it in. Right? Does that make sense? Now, how do I know I have an arbitrary graph? How do I know that I always have either case A or case B or case C, right? If it's not A or B, how do I prove that case C happens, right? Now, I'm going to prove to you that case C happens, right? How do we prove it? Well, as I was about to say, if U either has an edge down or up, if it has an edge down, then let's paint U red, say. And if it's an edge up, let's paint U blue, right? So now we have a string of pearls here, and each pearl is either red or blue, right? What are we looking for? We're looking for a place where there's a red pearl followed by a blue pearl, right? So here's a completely different theorem. Start with a string of pearls that every pearl is red or blue, right? What do we know about our first pearl? Well, it was red. What do we know about our last pearl? It's blue, right? So my theorem says there's got to be a place where it switches from red to blue. Why? Because it starts off as red, and suppose it switches to blue, then we're done. We found a switch from red to blue. But if it doesn't switch from red to blue, then it has to keep being red. So it keeps being red, 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 red. Well, if it switches to blue, we're great. If it doesn't switch to blue, it keeps going. Oops, bang, we banged into our blue. It's got to, at some point, it's got to go from red to blue.
Oh, I see.
Right?
Okay.
Isn't that fun?
Yeah, that makes sense.
Right? In fact, if we wanted to do a loop invariant, here's a fine, let me tell you a loop invariant algorithm, right? The input is a necklace of pearls. The precondition is that the first is red and the last is blue. The postcondition is you find consecutives where one's red and one's blue, right? What's my loop invariant? My loop invariant is that my left hand is moved in, right? I've been moving along. But the loop invariant also says that my left is always red and my right is always blue, right? I'm moving in, maintaining that this hand is on a red, right? And I always how can I make progress while maintaining the loop invariant? Well, I make progress by moving my hand over. If I reach a blue, then bang, I went from red to blue, so I'm done. And I exit and I leave. If I go from red to red, I've maintained my loop invariant that I have a red in the left and a blue in the right. Right? There's a good problem. I should put that on a test.